Hello, everyone, and welcome to our series on urban energy modeling with Dragonfly. In the previous video, we looked at a feature specific to URBANopt, which is what we're using to run our energy simulations, which allowed us to account for, in this particular case, electrical vehicle charging. But the specific technology that we used to accomplish this was an object called a mapper measure. In this video, we're going to similarly look at a feature specific to URBANopt simulations, but this one will be much more about post-processing the results of your energy simulation in order to get information about renewables and the most optimal arrangement of renewables for a given urban district. And to do this, we're going to use an engine that URBANopt links out to called REopt Light. And REopt Light, it is a standalone application. You guys can get to it actually just by going to reopt.nrel.gov. And there is a web app for REopt Lite where you can plug in various information about your site and get essentially a report of the most optimal deployment of renewables on your site, a cost optimal deployment of renewables, and the amount of money you can expect to get from that over the lifetime of a renewable system like photovoltaics or battery storage for that example. So we are going to essentially use our energy results of our district that we've run here and send them over to REopt using a specialized component and specialized features built within the URBANopt SDK. And we're going to use that to essentially understand what is the most optimal arrangement of renewables on for our given district here. So, all right, so you see our district. If I go back to our perspective view, right, we're just viewing this model from typical footprints. I think we'll keep our electric vehicles that we had in our previous video in our simulation as we try to understand what the most optimal arrangement of renewables is to serve these buildings and these vehicles. So first thing is first, if we go back to Grasshopper, we go over to the Dragonfly tab, you'll notice under the energy section, actually right next to the component we were using to actually run the energy simulation with URBANopt, there is a component called DF Dragonfly Run REopt. And so it's this component that we're going to use to essentially export our energy simulation results to the REopt Lite API, which essentially means that we're sending all of our simulation results to the servers that the National Renewable Energy Lab maintains in order to run the REopt Lite app. And we're going to get back results of the amount of renewables that would be recommended to install on the site and the cost savings that we can expect with that. So in order to run this component, you'll see that we need at least 3 inputs, 4 if you count the kind of run that we need to set to true. And the very first thing that we need to send is the GeoJSON. So this is the GeoJSON that we exported back here from our Dragonfly model. Right, and this basically contains information about where on the globe our model is, and and various pieces of information about about the site that we're working with. The next thing that we need is the URBANopt scenario. So you remember after we finished running our first URBANopt simulation, I pointed out this scenario file. Here is actually the chance that we're going to get to use this. So the scenario file is needed to essentially say which, what are the results of the simulation that we want to send over to REopt Lite. So every run that you do with the URBANopt SDK will have its own scenario. And so that's why we need to plug in this scenario input here for the REopt simulation. Okay, all right, and maybe let me make a little bit more room here so you guys can see. So we've got our GeoJSON, we've got our scenario connected. The last thing that we really need, discounting the run input, is that we need to connect up a URDB label. So URDB stands for Utility Rate Database. And that the utility rate database is essentially an online platform that houses all of the utility rates certainly for the U.S. and I believe also for some international locations. So if we want to find out what the utility rates are specific to this district, which if you remember I keep saying is in Buffalo, New York, the way that we can find those out, the way that we can get the ID of this or the label of the utility rates for Buffalo, New York, is by going to the REopt Lite application, like I said here. So we can go to reopt.nrel.gov/tool, And you'll see that actually the first section of the REopt Lite API, or the REopt Lite application, rather, that the web application that they have, is a interface to select your utility rate and your location, essentially, of your site. So I'm going to type in Buffalo, New York, and you'll see as soon as I select that, there'll actually be a suggested list of rates to choose from here, including a most likely rate, and many other options that probably exist within this region around Buffalo, New York. So I'm just going to take the first one that we have here. And instead of going and continuing on through the REopt Lite web app here, I'm going to click this little rate details thing that you can see below the actual electricity rate drop down here. And so if I select this, you'll see it'll take me to the OpenEI page for this. So this is actually the database from where that utility rate information is coming from. And there's a bunch of information on this rate. You can certainly, I'd suggest maybe you look through it. And you can find all sorts of information on OpenEI about the various different rates in different parts of the US, certainly, and I believe even of the world. Yes, because this is the International Utility Rate Database, the IURDB, right, that we have here. So in any case, the URDB label is actually this sequence of unique characters that's at the very end of the URL here. So this is actually what I need to go and copy to my clipboard and bring back to Grasshopper. So I'm just going to select that and then right click and copy that to my clipboard and go back to Grasshopper here so that I can plug in this string of unique characters to the URDB label here. So if I double click the canvas, type quotations marks and paste that into a panel, this is what I want. This is the URDB label that carries all the utility rate information for Buffalo, New York that I want to use in my simulation here. All right, so we have all of our results going through via the GeoJSON of the scenario. We have our utility rates set up. You can essentially dictate the financial parameters of the cost optimization that REopt Lite will run. These financial parameters are just the output of another component that you'll see under the energy section here, the DF REopt Lite financial parameters. I'm going to just take the default, which is using costs of PV that are pretty standard for today. And you'll see that you can also look at wind in addition to PV, battery storage, and generators on site. But I think this essentially has enough of what I need right now. So with this all set up, I'm going to take a Boolean toggle, and I'm going to connect it to the run because we know this is the last input. And as soon as I click run to true, you'll see a window will pop up which will essentially upload all of my results to the REopt Lite API and begin running that cost optimization. Now it's going to run this optimization at every single time step of the simulation that we ran. And I know by default, I think we use a time step of 6 in our simulation. So that's going to be 10 minutes, every 10 minutes. So it's going to take a while actually to run this, a few minutes for it to bring back results. So I'm just going to fast forward through this part. I'm going to set this toggle to true, and I'll see you on the other side once we get results back. Okay, and so REopt finished post-processing these results to tell us what our optimal arrangement of renewables would be, optimal arrangement of PV and storage, at least, are the two critical things that we're looking at here. And so the way that we can start to understand these results is first by taking a look at these values that come out of the run REopt component. So I'm going to bring up a panel here, and I'm going to connect up the values to values and make sure that we can see all these here. And of course, just these numbers, the way that they are, it's not exactly clear what they mean. So these are meant to correspond with the outputs of the parameters here. So I'm going to copy paste this panel, and I'm going to connect up the parameters to this other panel I've got here. And this will allow me to understand, if I make this a little larger, it'll allow me to see what these parameters actually mean, so I can start to interpret them and understand the results. Okay, so we're getting the year one cost of electricity in US dollars. These are demand costs and total energy costs. And oh man, all right, this is not really so exciting to see. So it seems that actually the optimal solution for our site here, using this Buffalo utility rate, is that actually that there's zero PV is essentially the optimum. So essentially what this is trying to tell us right now is that electricity is so cheap within this area, and the amount of solar energy available not enough to really overcome the cost of installing PV in the first place. And honestly, looking back at the particular utility rate that we picked, this is actually Niagara Mohawk Power Core. I know this is probably very cheap because Buffalo, New York sits right next to Niagara Falls, which I believe is where this utility power company is sourcing its energy. And Niagara Falls is a big source of hydroelectric power. So I can imagine energy is going to be particularly cheap, I think, in this part of the, with this rate that I'm using here. So I guess, I just have to accept for this particular project right now, I guess the optimum is to not really have any photovoltaics installed. So all right, so that's the case here. Perhaps maybe if I use some financial parameters, the cost of PV continues to fall. So maybe if I use some parameters for the cost of PV in another, 5 years, I might see something different. But let's try something, just a different simulation, so we can actually understand if, maybe if we didn't use such, there wasn't such cheap electricity available, could we get a different result? So I'm going to go back to the REopt Lite API. And I'm just going to pose the question, let's say, what if this site were, just a few hundred miles east over in Boston, Massachusetts? And now in Boston, Massachusetts, because I used to live there, I know the electricity is definitely more expensive than being right next to the Niagara Falls hydroelectric dam. So let me see. I'll pick this Greater Boston General Service rate right here. And I'm going to open up the rate details for this. So again, we'll get the URDB page for this utility rate, and I can copy this utility rate label if I want to understand what is going to be the optimal arrangement of renewables using this rate instead of the one in Niagara Falls and Buffalo, New York. So, all right, let's copy this over. I'm going to bring this back into Grasshopper, put it inside a panel, and paste it. Paste that URDB label, which you can see is different than the one above it, which is good. It means I copied it successfully. And now I'm going to run the REopt simulation using this URDB label. So I'm going to see you on the other side after this REopt simulation finishes. Okay, so the REopt simulation finished running with the utility rate of Boston instead of Buffalo, New York, and this looks a lot more exciting at least. Okay, so we can at least see that our total solar PV for our most optimal or cost optimal scenario, it's non-zero this time, and this specifically means that we should install almost 6,000 kilowatts of solar PV. That's probably enough, I'm guessing, just to cover the roof surfaces of the buildings that we have in our model here. So that's probably where that value comes from. It'll try and usually if it's profitable to put PV, it'll put them over all the roofs within the model. So all right, and we can begin to see what exactly, it looks like actually this is also very interesting to see. It's worthwhile to put some battery storage in, it looks like, in order to deal with the demand charges maybe that we might have in, or at least the gap between the supply of solar energy and the demand that we might have from the grid. So we should install, it looks like almost 1,500 kilowatts of battery storage with a full capacity of, it looks like, almost 4 kilowatt hours of energy. So, all right, so interesting. So we've got some results out of this that are make some sense. But now let's look at the part that would actually really convince a client who cares about dollar signs to invest in this PV. And we can see the probably the most important value for this is this NPV, this net present value. This is in US dollars, and obviously this could be converted to other currencies. But what this is telling us is that over the lifetime of the building, the lifetime of the PV, which I believe by default we run a scenario for 20 years. You can tweak that with the financial parameters if you wanted to say like 30 years or 10 years. But over the course of 20 years, we would expect to make about $15 million US dollars by installing this amount of solar PV and this amount of battery storage. So again, that's a very exciting finding. I mean, probably again, the only reason why we see this in Boston instead of Buffalo is because right, because electricity is a little bit more expensive. If you go a little bit further east. So again, and because the price of PV continues to fall, we probably expect a lot of locations across the globe to have positive values for this, for or non-zero values for the PV and the battery storage going forward. So, all right. So this is generally how to get the most useful pieces of information, out of REopt from the simulation results with URBANopt. I'm just going to show you a few other cool things that we get from the REopt Lite API, which are sometimes useful for making visualizations to explain, what is happening under this optimal PV scenario. And you'll notice at this data output here, we're just getting a set of data collections. These are time series data sets that contain various pieces of information about how this optimal simulation it runs over the course of the year. If I go and let's see if I look at these one by one, and I'm going to visualize these on a chart. I'm going to grab a native Grasshopper list item component so that I can select out each of these data sets one by one. And it looks like I have a total of, 18 of these. So I'm going to make a slider going from 0 up to 18 so I can scroll through these different data sets. And in order to visualize them, I'm going to use the same type of monthly chart that I use to visualize the EUI, right? The monthly EUI up here. So I'm just going to grab that from the Ladybug tab. I'm going to grab a monthly chart. And let's see, I'm going to connect up. I'm going to go over to our Rhino scene so I'll be able to see this. And I know it should be in the top view that I should be able to best see this chart. And if I connect up this first data set, okay, we're going to see our two charts are going to display on top of each other. So I'm going to use a different base point for this lower, this chart showing REopt results. Let's see, I'm just going to move it from the Rhino origin. I'm going to make a point that's at 0 and minus, we'll say minus 100 and then 0. I think that should be enough to avoid all overlap. And you can see you can just type in XYZ coordinates, and if you connect this to base point, the component's smart enough to convert that into an actual point in the Rhino scene, so we can see it separately from the other graphic. The other thing, so we're looking at, let's see, electricity produced total in kilowatts. I think I'd rather like to see this. It's showing you a kind of distribution over each day. And so I'm going to stack this data just to make it, a little more solid looking. So you see if I stack data in kilowatts, that should, yeah, I mean, it should just look a little more readable, I think. It's going to be the total in this case, the total, I think, quantity of kilowatts, maybe as opposed to the average that we were seeing before. Yeah, but still, the most important thing is to understand the profile. So let's see. So this data stream that we're looking at from the integer 0 out of this REopt component, this is the produced electricity. This is pretty much following the kind of bell curve you'd expect over the course of the sun rising and setting on a typical day. Next, we can look at the electricity load or the consumption of electricity. So we can see the highest, looks like the peak in electricity consumption is later in the day, probably in the afternoon. It looks like because the curves are lowest, probably it looks like around 4 a.m. or so, and highest in that afternoon. And the electricity demand, understandably, is highest in the summer. Makes sense because that's when the air conditioning is running. And let's see what else do we have here. We have the electricity that's going okay, the grid supplied electricity that's going to satisfy the load, the building loads. That's what this one is. And we have a few different other ones. So we have the grid supplying the electricity to the battery. It looks like this is probably to avoid some demand charges. Yeah, and we got a few different interesting data sets to look at here. I mean, we can just make an interesting one right now with the produced and the consumed electricity. So maybe I know that if I just zoom into the list item component here and hit plus, this will give me the consumed electricity. So I can hold down shift and plot both the electricity load and the electricity produced on the same chart. Probably it doesn't make sense to stack these like this. Maybe it's easier to think of the load as something that's negative and the produced energy as something that's positive. So, I can do that pretty easily by analyzing this data or sort of processing this data using some of the analyze components under Ladybug. So, for example, I can do an arithmetic operation on the, let's see, we can make the consumed data here negative. So if I can just connect this up to this LB arithmetic operation component, and then I want to essentially try and multiply this by a -1. So I can put a -1 inside of a panel. Importantly, I need to make sure that it's a number going into this component and not just the text -1. So I'm going to pass this through a number component so that I can plug in this as the other data stream. And then if the operator is just a multiplication sign, multiplication sign, like a little asterisk, that'll ensure, right, I'm basically just multiplying this data stream of consumed energy by -1. And so I can connect this to our monthly chart and then connect the produced energy. Whoops, I see these are two different data streams here. I probably need to, let's see, just flatten everything together to make sure that I'm not getting two separate charts here. So after I flatten this data and flatten that data, here we go. Now we're getting a cool looking graphic, right? So the blue is the consumed power, the produced energy, that's what's coming out of the PV in this optimal scenario. Right, so you can begin to see, I mean, obviously the PV is definitely not enough to make this particular area net zero, which I'm sure is a tough thing to do when you have things like hospitals and really high energy programs on this district. But again, I mean, it's certainly a significant fraction of that load is being met with this electricity produced. So all right, so this gives you a sense of how to use the REopt Lite components. Right, and how you can use them to find the cost optimal implementation of renewables on your, given the results of your URBANopt energy simulation and a URDB label to say what utility rate you want to use. So that's it for this video. Thank you guys for joining again, and I look forward to seeing you in the next one.